All right, so Module 7. Module 7 is about trig. And for those who've had trig before, it's going to feel different. Okay, we're really going to focus on the underlying ideas. And but my experience is that people that, after they've come through that, they're really appreciative of it, because all this stuff they learned in trig before, they had no idea what it meant and what it was all about. And so it's like, oh, now it all makes sense. Okay, so I think you'll appreciate this. Pathways does a really good job of exploring these ideas so that it's meaningful. Okay, and for you as engineers, that's especially important. Okay, so we got trig starts with angles. Okay, so first of all, definition of an angle: two rays with the same endpoint, called the vertex. So two rays that have the same common endpoint forms an angle. That's an object, right? An angle is an object. And then we talk about the measure of an angle. So we can ask this question: what does it mean for two angles to have the same measure? So how about these angles? Do any of these angles have the same measure? Any of these angles have the same measure?
Measure in length or measure?
Yeah, okay, so this is the right question. What does it mean to measure an angle? So what does it mean to measure an angle? Okay, so really, before we can answer that question, we have to ask, what attribute of an angle are we assigning a value to when we talk about measuring an angle? So what is it about an angle that we're assigning a number to when we measure it? So I'll just draw one here. So what is it about that angle that we're putting a number on? What attribute or physical characteristic? Adi?
Like its openness?
He's saying it's openness. How open it is. Other ideas? Distance between
two lines.
the rays. Okay, so we got openness, we got distance between the rays. Any other suggestions? What are we measuring when we measure an angle? What characteristic? How about length of the rays? Is it the length of the rays? No. Okay, so people are shaking their heads. Good. Okay. All right, so yeah, it's one of those two. It's either distance between the rays or it's the openness of the angle. It is one of those two that we're measuring. So what about distance between the rays? Yeah, even in this angle right here, isn't it the distance right here is short, right? But then out here, distance is greater. But this is the same angle measure, no matter if you're talking about being close to the vertex or away from it. Okay? So that leaves openness, and that's exactly what it is. So think of the angle as a door. Like one of the rays is the door, and the other ray is like the threshold of the door, or the wall line, okay? And so we're saying how open is the angle, or how far swung open is that door? And we're going to place a number on that. Okay, so order these from least to greatest openness, just so we get a feel. So which is the least open and which is the greatest? Talk to your neighbor. Which is the least open and which is the greatest open? So which is the least open? Khan. A, B, or C? He wants C. Agree with that? The least open. Most are agreeing. That's right. C is the least open. It's the closest to being shut. And which one's the greatest amount of openness? B. Okay, it's the furthest open, right? B, it's the furthest open. And so here this just underscores how it's not distance, right? Because look at the distance between the rays here. Okay, this is a greater distance, right? From there to there, between those tips, is a greater distance than from there to there. But C has a smaller measure because it's less open than B. Okay. So now the question is, how do we measure openness? How do we assign a number to the openness of an angle? Okay, and so the common thought is, oh, it's just degrees. Well, the degrees is just a unit, so it's really that's like kind of putting the cart before the horse. Okay, so how is it that we come up with degrees? That's what we're saying. How do we get a number that specifies the openness of an angle? Omar has an idea.
Yeah, usually this how long or what's the length of the two rays?
The length of the rays.
Yeah. You could use that.
Okay. Yeah, so that doesn't the arrow, he's saying the arrow means that they just continue on forever, right?
Yeah, in a way.
Okay.
But there's like, for example, in A, there is a certain point where it stops. You can like measure that, and then you can find the answer.
Okay, so here's what you're saying. I think what you're saying is it depends on how far from the vertex you are. So that's part of it. That's part of measuring this openness. Part of the openness is looking at how far away from the vertex that we are. Okay? Other ideas for measuring openness? Alex?
It's more of a question. Right now, when you measured C, you took it as in it was really small, but can you look at it from like the other way and it'd be like really, really big?
Right, so I didn't you're right. I didn't specify which side. Excellent. Yeah, that's a good point. So by looking at this, the assumption was that the openness is swinging from here to here, and then swinging from here to here, and then swinging from here to here. Right. But what you're saying is it's possible, couldn't this side have swung all the way from here around like this? Yeah. Yeah, absolutely. Yeah, it's good. So if C had started, if this was the door right here, and it started here, and it swung all the way around like this, then yes, C would have the greatest openness. You're right. That's right. Okay, so other ideas. How do we assign an actual number to the openness of an angle? Alex?
Well, the more you open, I guess, the door,
Okay.
it's kind of making a circle.
Okay.
So you can use, we have certain information already on circle that you can use to measure.
Okay, so these guys are both getting onto it. So it has to do with circles, and it has to do with looking at how far you are from the vertex. And so if this was the center of the circle, say that's the center of a circle, and say that was where the circle went through that thing, what would that distance be? That'd be the radius, right? Okay, so now we're getting somewhere. So measuring the openness of an angle has everything to do with circles, putting the vertex at the center of a circle. All right, so let's do a little exercise here. We're going to design a pizza cutter. Okay? So here's two possible variations, but they're really both the same thing, okay? There's, when you have a wedge of pizza cut into the middle, it forms an angle, right? It forms an angle. Our two rays are our cuts. And so what we want to do here is we want to design a blueprint that gets us 9 equally sized wedges. Okay, so we want the angle to be just right. The openness of the angle to be just right, so we get 9 equal sized pieces. Okay, but you don't have a protractor, you don't have any formulas. Okay, so it's like you're an architect, you have the common desk supplies, like a pencil, ruler, tape, scissors, string, etc. And we want to design. So either they're both two versions of the same thing. How do we design a blueprint for a pizza cutter that's going to give us 9 equally sized wedges, or get that openness correct? So get a partner and kind of think through this and think through a strategy. Write out, take notes on this. Write out the steps that you would do in order to make a blueprint for this pizza cutter to get 9 equally sized wedges. Okay? Go. Sure, he wants a pizza. I can do it. There you go. I was all ready. Does that make you hungry? Okay, then we'll look at this one then. With that. And do we have circles actually?
Yes, good.
I think this is in your workbook. This is on page 259. This is basically number 2 on page 259 if you care in your workbook. It's number 2 on page 259. Yeah.
Do you mean equal areas or equal? Has to be triangles.
This is about angles, right? This is about getting the right angle so that all the pieces have the same area. Yeah. But it's about the angle, right? No, that's not. It's just we just want to design the blueprint. You don't have to. We're not measuring yet. You just want 9 equally sized wedges. You don't have to. You don't have to know what their area is or what the angle is or any of that. Just 9 equally sized wedges. Oh yeah, it's like the second homework equation. Okay, let's see how it went. Aaron, tell me what you come up with. Yeah, were you thinking about it? Okay, how about Brian? Did you come up with anything?
All I got was take the pencil and string, hold the string down. I'll circle it.
Okay, so wrap the string around the pizza? Is that what you're saying?
Tie the string to the pencil.
Okay.
Hold the other side of the string down.
Yeah.
Just outline the circle.
Oh, you're going to draw the circle with a pencil.
So it's fast.
Okay, and what would you do from there?
That's as far as it
That's as far as you got. Yeah, Alex.
I pretty much grab the string and wrap it around the pizza.
Okay, so yeah, so we're going to take the string and wrap it here. Do my best here, stay close.
And then you would pretty much lay it on a straight line and then measure it with.
All right, so you're going to take that string and you're going to stretch it out straight. Okay.
Measure with the ruler the total distance and then divide it by 9.
Okay, and then measure the length of the string and divide it by 9. Who wants to do that? Somebody else do this?
You did it.
That's what you did? Okay, so let's see how well I do here. So maybe like, is that 9? How did I do? 1, 2, 3, 4, 5, 6, 7, 8, 9? Like that, right? So you marked off 9 equal lengths on that string that you had wrapped around. Okay?
And then you wrap it around the pizza again.
You must go back to the pizza. Is that what you did? Yeah? And so then those marks on the string, let's see if I can do this at all any good here. something like this. Wow, it's hard. I blew it twice, but anyway. All right, so you got those. Oh, yeah, it'll be here too. So 1, 2, 3, 4, 5, 6, 7, 8. Not too bad. Okay, and so then we take those marks on the circumference, and since they're equally spaced apart, they'll tell us then how to design that blueprint. To get us the 9 equally sized spaces. So then we'll find the center and draw lines into the center. You can see that. And so what are we doing then? So then what's the underlying idea of this exercise? That measure of the angle is based upon what? What is the measure of the angle based upon? What's the point of this exercise? He said circumference of the circle. So if we have an angle, so what is it about the circumference that does?
How much of the circle is there saying?
How much?
The circumference covers the circle.
Okay, so you're looking at, say, for this angle right here, are you looking at like this right here? So we're looking at a fraction or percent of a circle, right? Or a fraction of their circumference. You see that? That will denote an amount of openness. A fraction of a circle would denote an amount of openness. What if we had done this on the larger pizza? So we started with a longer string around this pizza, and we did it again. We marked that string off into 9 pieces, and then we put it back on, and we got our... Would the angles be the same or different? Do you see that they'd be the same, right? So by looking at a fraction or percent of the circle or the circumference, we can pinpoint an amount of openness. This is a really powerful idea. Does it make sense? Okay, so let's summarize that. So what is the measure of an angle based upon? It's based on percent or fraction of a full circle. That's the underlying way that we're going to build up the ability to measure an angle. The percent or fraction of a full circular rotation. That was the point of the pizza thing. To see that we could take that circumference and we could stretch it out and chop it up into 9 equal lengths, put it back on, and that would give us, each angle would be like 1/9 of the circle. Okay, so or circular arc length relative to circumference. So both of these are ways of looking at measuring an angle. So what was our angle for the pizza cutter? So that angle that we found, whatever it is, we had the pizza. Something like that. So that was based on what? 1/9 of the circumference. 1/9 of the circumference right there. And so we can call that angle, we can start by saying, well, that angle's 1/9. Meaning 1/9 of a full rotation, or 1/9 of a circumference. That's how much openness it is. So here's some practice. So what about this one? 1/4, right? So if it was this right here, we're looking at that angle right there. That would be a 1/4 or a 25. We can use percent if you want. So we can call that angle 25%, or we can say it's 1/4. Okay? Here's an angle. How about this one? It's not 1/3. Why not, Alex? What's this one instead?
2/3.
So what if we looked at that? How much openness is that? Or what circular arc length relative to circumference do we have? 2/3, 66 or 67%. Last one, this one here. So once I give you, it's hard to see, but once I give you the circle and show you how it's a fraction of a circle, then you can see what it is. What is it? 1/6 or 17%. Okay, so now we can talk about, now that we have this kind of underlying idea that the angle measures can be based on percent of the circle or fraction of the circumference, we can talk about degrees. What are degrees? So this is, turn to the next page, 260. So this is not a well-stated sentence because the angle is the object and 1 degree is the measure of the quantity. So what does an angle with measure? What does an angle with measure of 1 degrees represent? Based on what we just talked about as our underlying idea for measuring angles as percent of the circle or fraction of the radius. Patrick, did you want to say?
I was just going to say, because we know that there's a circle of 360 degrees.
Okay.
It's 1/360th.
Okay. It has to do with 1/360th of the circle. So now, what about the angle then? That angle, so what about the angle's openness then? So the angle's openness, yeah.
It would be that the angle measure would describe an arc length on the outside of the circle, around the circumference of the circle that was like 1 out of 360.
Yeah, okay, good. All right, pretty good. Yeah, so here's what this looks like. I'm showing you an openness of 1 degree. I'm showing you openness. We'll zoom in on it here. Okay, so that's an openness of 1 degree. And so an angle with that measure, 1 degree of openness. Did you just see it? It's been up for a little while. All right, so an angle with that much openness, it has to do with how much of the circle that those rays cut off. So right there is what amount of the circle? Patrick said 1/360th of the circumference. Okay, so an angle with a measure of 1 degree has rays that cut off 1/360th of the circumference of the circle. All right, and so here's a good definition. An angle with measure of 1 degree, whose vertex is placed at the center of a circle, has rays that subtend. So here's this word that you're going to see a lot. An arc length that's 1/360th of the circumference. So given the context here, what do you think the word subtend means, given the context? Tim, do you have an idea? What does subtend mean, given the context of this definition? So the rays subtend an arc length. What are the rays doing? They're subtending 1/360th, an arc length of 1/360th. What's that? It's the distance that is between the rays. Were you gonna say something? Were you gonna? No. Was there a hand up here? No. Let's see. Yeah, Alex. Yeah, but what do the rays do? They subtend. What does that word subtend mean? It's like they cut it off, right? It's like they cut out a piece of the circle. That's what subtend means, like cut out a piece that's 1/360th of the circumference. And so you'll see this in the on the web work and in the Pathways workbook. This word sub-10. So the rays cut out an arc from the whole circumference, which I've shown in blue there. I've highlighted in blue. Okay, so what about 36-degree angle? An angle with a measure of 36 degrees. Nadine, can you explain what would an angle with a measure of 36 degrees be?
It would be 36 over 360 of the circumference, so it would be 1/10.
So the angle is such that what? That's right.
It's the angle such that the vertex axis is 6 of the circle, has raised us 1/10, the arc length 1/10 of the circumference.
Right, if it's 36 degrees, then those rays are going to cut off or subtend 1/10 of the circle if it's 36 degrees. Okay, any questions? So I think you've got, what do you have there? Is it 10 degrees or something?
10.
B? Yeah, so write out a good definition for the meaning of an angle with measure 10 degrees. That's part B there. The top of, what is it? 360? 260. Top of 260. Write out a good definition for the meaning of an angle that's 10 degrees. All right, who thinks they got a good definition? Anna, did you get a good definition? Tell me.
The angle of 10 degrees with the vertex axis at the center,
Mm-hmm.
and the rays that the arc length of 1/36 of the circle.
Okay, so she's saying if an angle is measured 10 degrees, the rays will subtend 1/36 of the circumference of the circle. Is that what you put? That's it. So the rays will subtend 1/36 of the circumference. Okay, so that's degrees. Let's look at a different way to put a number on angles. So the degrees isn't the only thing. So let's look at a different way. Wow, it's not showing up at all. Can you see the green circles? That's okay, just as long as you can see them. Barely is fine, but you can see them. In the back, can you see them? Question?
Why it would pick 360?
Okay, so that's a good question. Where did the 360 come from in the first place? Anybody know the origin of 360?
I just know, I think I know who did it, but I don't know exactly.
Yep, some do the sun. So I believe it was the Babylonians. And so by their estimation, the year, they came up with the year was 360 days.
Okay.
Instead, when we know it's 365 or a little bit more than 365 and a quarter, right? So they came up with, by their measurements, that it was 360. But then this number 360, in terms of breaking up a circle, was very convenient because it has so many factors. 4, 2, 3, 4, 5, 6. I think those are all factors of 360. So in terms of breaking up the circle, all very convenient. Yeah, but I think it was their calculation that the year was 360 days long. Okay, which is pretty close. Yeah, pretty good. Okay, so here are 3 circles. So in that, I'm showing you something here. I'm going to add something to the picture. What am I showing you there by that purple bar? What am I showing you by that purple bar? A radius. And can you read the numbers? These are just integers, right? These are just whole integers on the scale. So the radius of that first circle is 1. Okay, now watch it. Ready? So I'm going to take that radius and I'm going to take it from this normal position from the center out to the edge. I'm going to preserve its length. I'm going to lift it off and I'm going to wrap it onto its circle, keeping its length the same radius. Okay? This is a really important idea. I'm going to take the radius, do it again. Take the radius, lift it up, but don't change its length, and wrap it on its circle. Okay? Next circle. What's the radius? 4. It's the blue. The middle circle is the blue circle, okay? So the radius is 4. I'm going to do the same thing. Take its radius, preserve its length, and wrap it onto its circle. Okay, burn this image in your mind. It's really important for what we're doing. And then finally, the last circle has a radius of 6. There it is. It's red. I'm going to pull off that radius of 6. I'm going to wrap it on its circle. Okay, so now what I want you to do is have a short discussion. And I want you to come up with 2 things about those 3 arcs. So you got 3 arcs now to look at. 2 things about those 3 arcs that are different. Color does not count. Okay? 2 things about those besides color that are different. And 2 things about those 3 arcs that are the same. So I'm asking about the arcs, okay? I'm asking about those arcs, the purple, the blue, and the red arc. What are 2 different things about those that are different, and then 2 features about those arcs that are the same, okay? So take a couple minutes, have a conversation, and come up with it. Go. Okay, Jared, did you come up with something about those 3 arcs that are different? One thing. The radius of the circle they came from? Okay, so he said that one thing that's different about those arcs is the radius of the circle that they're on. Or the radius of the circle they came, yeah. So the radius, the respective radius. Those are all different. Each radius is different. Good, okay. What else is different about those 3 arcs? Somebody new. Brooke, did you come up with someone else? The fraction of the whole circumference is different for each of those. Okay? Not quite. So what's something else? Walter, something else that's different. Yeah, this is the length of the arc, right? Length of the arc is different. Anything else that you guys came up with that was different about those three arcs? Those are the two main ones, but there could be others. Anyone want to offer up anything else? Okay, now what about fraction of the circle fraction of the circumference that the arc lengths mark off? Same or different? Yeah, so it was a good one, Brooke. It's just that they're the same, not different. Do you see that? Yeah, the fraction that the arc length maps off on its circumference is the same fraction each time. What else is the same? Let's see. Justin, did you get another one that's the same?
I said the degree of the arc length.
Okay, so it sounds like you're kind of talking about an angle. Are you talking about an angle when you say degrees? That's okay. Is there some angle that's kind of emerging when we draw these three arcs? Do you see an angle emerging from that?
Yes.
Right, and so is the angle openness the same for all three?
No, it gets bigger.
The openness gets bigger.
No, it's the same.
What do you think? Yeah, so the same for all three would be like the openness of the associated angle. Openness of the angle that subtends these arc lengths, right? Openness of the angle that subtends the arcs. Okay, so if the fraction of the circumference is the same, and the openness of the associated angle for each is the same, subtending the same amount, then is arc length, radius, so is using the radius as arc length, is it a valid way to form the basis of measuring an angle? Yeah, because this goes right back to what we said before. So using the radius length to kind of mark off angles is totally valid. Why? Because we're preserving the fraction of the circumference. You see that? No matter which radius we pick, we preserve this same openness. So using the radius wrapped on its circle is a valid way to measure angles. So let's define the angle first of all. So the angle, one side of the angle, do you see, is the positive x-axis? So I'm highlighting that there. You see that? Okay, that's called the initial side of the angle. Okay, it's the positive, or it's the positive x-axis. Okay, but the language you're going to use most of all, we're going to use this over and over again, is that this angle here, or this initial side of the angle, is at the 3 o'clock position. So you imagine these circles are like a clock. That would be at 3 o'clock. So we're going to use this language a lot. The 3 o'clock position. In the next couple weeks, we're going to use this over and over again. Our initial side of our angle is the 3 o'clock position. Okay? And so then we're going to say, starting at the 3 o'clock position, we're going to sweep an angle counterclockwise. Okay? So we're sweeping from the 3 o'clock position counterclockwise, and then where we stop that's the terminal side of the angle. So the initial side is the positive x-axis, and we call that the 3 o'clock position. And then we're going to sweep counterclockwise, and wherever we stop, that's the terminal side of the angle. So this is a very conventional angle that we're going to use throughout Module 7. The angle swept counterclockwise from the 3 o'clock position. We're going to say that a million times. The angle swept counterclockwise. CCW means counterclockwise from the 3 o'clock position. Or from 3 o'clock. Okay, the angle swept counterclockwise from 3 o'clock. And so, what arc length are we cutting off with the angle that I'm showing right here? We're cutting off an arc length of 1 radius length, right? In all 3 cases, that angle cuts off 1 radius length. So, using radius length as a basis for measuring angles, we call that the amount of openness. We use the same number as radius lengths, and we say that is 1 radian. So 1 radian is the measure of an angle whose rays cut off 1 radius length. Did you catch that? 1 radian is the measure of an angle whose rays cut off 1 radius length. That's what a radian is. Okay, so what is, here I'm showing an angle that cuts off 2 radius lengths. So this red arc is 2 radius lengths from its circle. How long is that arc length? How long is that arc?
2 radians.
Taz, how long is the arc length? It's 2 radius lengths. Is there another way, Fuda, to say how long that arc is? It's 2 radius lengths. What else is it in terms of its length? Two times, right? Well, what is 1 radius length in the red circle, in that outer circle? What's the radius length? What is it? What's that? 6. So how many units long is that? 12. So that's 2 radius lengths. It's also 12 units long, right? Because each radius length is 6 units. Okay, so if each radius is 6, then we're going to go 6. There's 1 radius length, and we're going to do another. So we get 12 total units. But both are valid ways to measure the length of that arc. 2 radius lengths or 12 units. Okay, so now I'm going to measure off 3 radius lengths. Okay, there's 3 radius lengths swept counterclockwise from the 3 o'clock position. So I want you to make a chart. And here's what's going to be in your chart. For the purple, for the blue, and for the red, I want you to write down what the radius is. Okay? And then the angle's openness in radians, which is denoted theta. Okay? So theta is the angle's measure of openness in radians. Okay? And then the last column in your chart will be S, and that will be the arc length in the axis units. Okay? Arc length in axes units. So you have 9 values to fill in this chart here. Is the task clear? So let's make sure we know. R is the radius of the circle that you're talking about. Radius. Theta, that theta is Greek theta, stands for the angles measured in radians, the openness in radians, which we just talked about. And then S stands for the arc length. Stop doing that. S is the arc length in the axis units. Okay? So, go for it. So fill out this table. I'll take attendance. And work together. Megan can circle around and troubleshoot with you and check your work. Is the task clear? Yeah.
Couldn't you also measure it like in terms of diameter? Because you got like two radius, right? So that's one diameter. So.
It's not conventional. So yes, you could. You absolutely could. But the most common thing to do, because radians is based on measuring in radius lengths. But that'd be a legitimate thing to do. Yeah. It's just not often done. Other questions?
So for theta, just 1, 2, and 3. Like 1 radians.
No, for what you're looking at. For the image that you're looking at right now. So everything you're doing and you're filling out this table is for the current static image on the screen. And what I told you was, I've now flung out 3 radius lengths. I've swept out 3 radius lengths on all 3 circles, counterclockwise from the 3 o'clock position. Is it clear? Is the task clear? Work together, get help from Megan. Okay, so is it making sense? Are you making progress? Solo, where did I lose you? Because I probably lost a handful of other people in the same place. So, okay, you're just gonna ask Megan. Okay. Yeah.
For the openness, did we just write a number?
These are all numbers. The whole box is filled with numbers. Yeah.
Because I was thinking of putting maybe an R in front of whatever number because we're measuring the openness and lengths of radiuses.
No, maybe, but you can put just pure numbers, values in all 9 boxes based on what we've talked about. And based on this, what the situation is right here. Okay, so Joe, did you get the first row on the table? The purple circle. Did you get that? No? Okay, well, let's do it together. What's the radius in the purple circle? 1. Okay? What's the openness of this angle in radians? Joe. So, no, where do we get radians from? So did you catch it from before? Where do we get the angle measure in radians from? Okay, so this kind of, I talked, but maybe didn't make it. So here was what? 1 radius length. What was the angle? No, not 60. 1 radius length gave us an angle of how many radians? 1 radian. 2 radius lengths. 2 radius lengths swept out. That angle that cuts off 2 radius length is an angle of how many radians? 2 radians. Where do radians come from? The number of radius lengths cut off by the angle. So here we are at 3 radius lengths cut off. So if 3 radius lengths, we got angle that cuts off 3 radius lengths, what's its measure in radians? 3. So that, exactly. What is the arc length in the axis units? Joe, so how long is that now in axis units? How long is that purple arc? 3. We made it. Okay, how about the blue arc? Who's up? Jonathan. Blue arc, tell me the radius. The radius is 4. What's the openness in radians? Still 3. What's the arc length in axis units? 12. I'll stop right there. Anybody have a question? Does it make sense? So each radius length is 4. We're going to go 3 radius lengths, and so the total length of the arc will be 12. Shola, talk to me about red. 6 is what? The radius is 6. Openness is 3 radius lengths. 18. How do we do? Okay, so here's the deal with this center column here. There's 2 ways to look at that number. What's one of the ways we're interpreting? It's actually, we're kind of interpreting it 2 different ways. So what's one of the ways we're interpreting that number? Ahmed?
Define 3 by 1.
No, just the meaning. Where's that 3? 3 what?
How many radius do we have?
Radius lengths on the arc, right? So this is radius lengths of arc length. But we're saying that number is the same as what? We're also interpreting it how else? Austin. That number of radius lengths is the same as what? No idea. Diana. The number of radius lengths cut off by the arc is the same as the number of what? Okay, Corey. Well, we're using radius length as a unit, so we're saying that we're going to cut off 3 radius lengths. But what else? How else are we interpreting that number 3 then? Jaden. Radians, right? Radians is a measure of, it's not a measure of arc length anymore. What's it a measure of? No, not arc length. Openness. In radians, okay? So we're seeing that number, that theta number, 2 different ways. We're seeing it as the number of radius lengths. We're also seeing it as the amount of openness in radians, because that's where the openness in radians comes from, the number of radius lengths. Okay? So what I want you to do is make a formula that brings together r, theta, and s. So if we were to bring together r, theta, and s, we want to write a mathematical relationship of those 3. What would it be? R, theta, and s. What would the relationship between r, theta, and s be? Audie. No idea. That was what the table was for.
It's the formula.
Right, the formula, right.
It's
Oh, well, you just remembered it from before. I was hoping you'd use the table to come up with it.
yeah. Arc length is equal to the number of radius lengths times the radius length.
Right. Yeah, so how far we are, the length of that radius is going to be how long each radius is times how many radius lengths. Should make sense. The length of that, say the red arc is 18 because it's how many radius lengths? 3 times the length of each one, 6. So S equals theta R, or R theta, okay? S equals theta R. And so in this equation, it helps to think about theta as number of radius lengths. Numbers of radius lengths because you've got how many radius lengths? The length of each radius multiplied together, it gives you the total arc length. Okay, so what I want you to do is, all right, any questions? Really key stuff. So we got 2 ways to measure angles. By degrees, we defined what a degree is, and now by radians, we defined what a radian was. Okay, so we have 2 different ways to place a number on the openness of the angle. All right, so let's look at I want you to, can you read that? Make it bigger. Estimate the position of the terminal side. So let's just zoom in here. No, let's not do that. Let's do something else. Okay, so how about this? So this is 3 radius lengths to get this far around the circle. Okay? So how many radius lengths to get exactly halfway around? So here's 3.09. So that's 309. That's not enough. That's not enough radius length. And then if I go my next click, it's 3.19. That's too much. So it's something between 3.09 and 3.19 radius lengths to get exactly halfway around. And some of you are already thinking you know what it is. Okay? So to get exactly halfway around, so the way I've got this set, it's got to be something between 3.09 and 3.19. Well, let's split the difference. What's halfway between those two? 3.14. Let's try that. I'm going to put in 3.14. Okay, did we make it? Let's see here. Oh, that's not what I wanted. Gee whiz. I wanted this. Did we make it? 3.14. Get out of there. Go away. I can't get rid of it. Okay, anyway. So, was it enough? Here's the exit. Doesn't make it far enough. It's a little bit more than 3.14. So now you guys have an idea. 3.14, 1, 5, 9. Okay. I'm going to put that in. 1, 5, 9, 2, 6, 5, 3, you said? Boom. How many radius lengths does it take to get exactly halfway around the circle? Pi. That's what the number pi means. It's the number of radius lengths to get exactly halfway around the circle. You learn something new every day. All right, you want to watch the video? 20 seconds. Let me shut up.